Awesome. So thank you so much for the invitation to give a talk. I'm very sorry that I was not actually able to be there in person. I had been hoping to be, but you know, things happen. So anyways, yeah, this is basically what I'm going to be talking about. I just want to give a quick shout out to some of the colleagues that I have that have worked on this. So a lot of this work has also been driven by Caroline Muthmuller, who is a postdoc at UCSD and is actually going to be starting at UNC in the fall, as well as Varun, Jinji, and Harish in various aspects who are all grad students at UCSD that we work with, and then the generic funding thing. Okay, so what is the question we're interested in? What is the problem that I want to talk about today? Sorry, there's a weird, hold on, sorry. The share thing was blocking a lot of my own slide. Okay, so the question that we were interested in talking about is a little different than your standard supervised learning problem. You know, normally for supervised learning, you think about trying to build a classifier where your points come from some vector space. I want to instead think about the problem of trying to build classifiers on distributions or on point clouds that are sampled from those distributions, okay? So that's basically the issue that we're considering here is, you know, you have mu k some probability distribution or some finite sample from it. And I really want to think about a setting in which each one of these mu k's is maybe stored in various places. The reason I'm interested in this is because there's some cool medical problems that one can formulate as building classifiers on point clouds. And I'll give a brief example of one towards the end. You know, in that setting, you wind up having a lot of sort of distributed storage, right? So what I want to think about is problems where I can draw aggregate statistics from these distributions and only have to communicate some low dimensional set of values, right? To then be able to build whatever classifier I want. So this is roughly the idea. And obviously, you know, building a classifier on a distribution, there's a lot of ways one maybe could think about it. I want to think about it in a way of embedding a distribution into some nice Hilbert space so that then I can just use some, you know, off-the-shelf classifier, okay? And again, because I'm thinking about these as being in different places, or, you know, I don't want to have to load all of my distributions onto a central server. I don't want to have to do things that involve pairwise comparisons, because that's obviously not going to be, you know, pairwise comparisons of where I have to compute, you know, n choose 2 statistical distances or something like that. Okay. So this is kind of roughly the setting, and the follow-up question to this is, all right, well, if I can build a classifier, I also want to think about what is simple distances between these representations actually approximating. Okay, what is the geometry of the space that I'm actually inducing? Okay. And so, like I said, there's a couple of examples that I'll kind of come back to. One is this medical test flow cytometry, which I'll talk about a little bit more at the end. Another is just a very simple example of, you can, you know, one way to think about an image is as a, you know, point in 784 dimensions or whatever the number of pixels is. Another way to think about it is it's just some density on a unit square, right? And then I want to be able to talk about how to, you know, build a classifier on that density. That's the idea. There we go. Yeah, so the goals of the model that I want to think about are, like I said, that I can sort of work in some distributed way. I don't have to load all pairs of distributions. I want to be able to use simple classifiers. I want to understand the geometric structure of the latent space that we're creating. And also, we really want to make sure that whatever statistics or whatever we're creating are robust to, you know, perturbations, simple transformations of my distribution. You know, if I shift my distribution a little bit, it shouldn't really affect anything too much. Okay, that's the goals. So now what I'm going to do is talk a little bit about, you know, how we're going to actually approach this, which is through the guise of optimal transport. So, you know, I can't see who all is in the room, so it's very possible that I don't need to describe this at all. I'll go through it very quickly if that's the case. But basically, so I want to think about the problem of optimal mass transport, which, you know, if you've never seen it before, the idea is you have some, you know, probability distribution, you can think of it as a pile of sand. Some other probability distribution, you can think of it as like a hole that you're going to move the sand to. And we want to figure out the way to move the sand not just that it is a transport, but that it is the optimal transport in the sense that it minimizes the work that we actually have to do. Okay, and work is defined as, force over time kind of thing, or force over distance kind of thing. So that's the basic idea. We're actually going to focus on Wasserstein 2. For those of you that are very familiar with this, the reason we're going to focus on Wasserstein 2 is because of Renier's theorem, basically the fact that any optimal transport map can be expressed as the gradient of a convex function. That's actually very critical and useful in a lot of what I'm going to do here. So this is not the best way to write Wasserstein 2 because right here, for the moment, I'm going to assume there's a transport map, and then I'll explain why map and not a coupling, and then I'll explain why that's fine. But basically, the Wasserstein 2 is just the fact that we are, for every point x, creating some transport of it, looking at the cost that it took to transport. The cost here is in distance squared, and then integrating over the base measure mu. And all of these t's are measure preserving maps. Okay. And so that is the distance, but also we're going to actually express not just the map itself, but we're actually going to be in particular interested in the argmin of this. And that's the transport map. Okay, how did we move from mu to nu? Okay, and we're going to denote this as t mu nu. There's a whole robust theory on when this exists, when this is unique, all of this. We're going to be focusing in a setting in which the source distribution is absolutely continuous. I'll explain why that's not a problem. But in that setting, then we can actually say there exists this map. Okay. And I should say that obviously in optimal transport, there's a way to generalize this to this idea of mass splitting. One piece of sand gets split in two and moved to two different places. That would be generating a coupling. We're not going to talk about couplings now, but I will just kind of comment that a lot of sort of ongoing work that I'm doing in my group involves generalizing everything I'm talking about here to particular couplings, mainly using synchron optimal transport, if you're familiar with this. Okay, so why do we want to think about optimal transport? Well, a pro of optimal transport is that as a distance, it scales very nicely with basic operations, scaling, rescaling a distribution, shifting a distribution. What's a problem with this? Well, computing that optimal transport and the map can be relatively slow, which is going to be a real problem if we wanted to do all pairs of distances, right? That'd be n-choose 2 expensive calculations, which is not doable, right? But also the downside of optimal transport, at least as one normally thinks about it, is that that's giving you a distance. It's not giving you an embedding. It's not giving you a set of features that you can use for a classifier. Okay, so that's really where we're going to focus in this talk, is how to take the idea of the distance and turn it into something that is an embedding where we can then build classifiers. Okay, so how do we do this? So the idea is to go through what's called linearized optimal transport. So I will just give the caveat right now. Caroline and I are not the first people to think about this. This was actually, there's a lot of different communities that talk about this in very similar ways. We came into this community through the work of Gustavo Rode, who worked on a lot of this stuff without really much of the theory, and then establishing some things in one dimension. Okay, so what is the LOT embedding? So the idea is we're going to create a map from the space probability distributions to L2 on RD by basically taking the distribution to the transport map from a fixed sigma to mu. Okay, so the idea here is we're fixing one reference distribution, and for the moment we're going to say we have complete control over that reference distribution. And then we're saying, all right, I'm going to represent this data set as how do I transport sigma to that data set? And then I'm going to represent this data set as how do I transport sigma to that data set? Okay, so basically, down here, you can think of it as we build the features, which is this transport function of how do we transport from the green distribution to this blue distribution or this red distribution. Okay. And that is the LOT embedding. Okay. And another way to think about it, and this is kind of how I like to think about it, is if we just have mu1, mu2, mu3, there's no sort of registration, right? Each of them has points, but we don't have a registration between the points. So what we're saying is, I'm actually going to impose a registration. And here's how we register it. We build the optimal transport from sigma to mu1 and the optimal transport from sigma to mu2. Well, each point from sigma gets mapped to somewhere in mu1 and it gets mapped to somewhere in mu2, right? Now I'm going to say those points are registered with each other, okay? And then that allows us to do simpler calculations, okay? So this is the idea, is that we're going to use this transport map as our feature space. But this obviously leads to questions. It leads to a question of how do we pick the reference distribution? What are natural actions we can do on mu that will, translate nicely with this LOT embedding? What is the distance that we're inducing, right? You can think about saying, all right, well, I could define a new distance between mu and nu. It's the transport map from sigma to mu minus the transport map from sigma to nu, and then just take Euclidean distance, or weighted Euclidean distance. Is that anywhere close to the optimal transport distance between mu and nu? And then finally, we have this central question, which is, what types of classifiers can we build? When can we build classifiers easily? When can we build low complexity classifiers? Okay, that's the setting.
Sorry, Alex, I have a question.
Yeah.
The map T, the transport map, might depend on how far the supports of two measures look like. Sigma and mu.
Yes.
And instead, I mean, the internal structure, let's say, of those distributions, how they look like internally around their mean, yeah, it counts also, but
this is a very this is a very good question, and actually maybe in like 1 or 2 slides from now I'm roughly going to address this.
Would you like to center everybody or no?
Well, you can, but it actually winds up that shifts are not going to affect this problem at all.
Really?
Yeah. So shifts are actually an operation that will basically cost us nothing when we come to talking about distances and talking about building classifiers. Yeah. So you could think about centering everything, but you actually don't have to, which is something I'll talk about in just a second.
I see.
Yeah. Similarly with rescaling, this is actually kind of part of what we're wanting to talk about here. Okay. So anyways, these are the sets of questions, and I want to always put this out there every time I give this talk. The same week that we put up something on archive, Gustavo Rode and Akram Aldrubi and a couple other people put up a similar paper on archive. They're slightly different in scope, slightly different theory. We addressed this idea of what I'm going to call perturbations. But we were sort of working on these ideas concurrently. So I always like to just sort of make that claim. But yeah. Okay. So anyways, so this gets into actually addressing that question. I want to think about what operations I can do to mu, or all of my mu's, that are going to be easy to work with. Okay. So what families of group actions that I could apply to my distribution interact nicely with optimal transport? That's like very roughly the question. Okay. So first off, I just want to say, say you had some function, some transformation S. It's easy to show that if you applied that to the optimal transport from sigma to mu, and then applied that to sigma, you would get S applied to mu, right? If you haven't seen this this sub pound before, that's a push forward. It basically just means you are, intuitively it means sample a point from mu, apply S to it, do that for every point you sampled from mu. This is now your new distribution. anyways, so it's easy to show that these two things are equal, but the problem is that the optimal map? Okay, so another way to think about that is, if I went from sigma to mu in an optimal fashion, and then move forward with S, that's one way to get to S push mu. Another way is to build the optimal map from sigma to S push mu directly. The question is, when are these two things the same? When is it optimal to move to mu and then to S? Okay. And it winds up by understanding this, it'll actually make a lot of it'll make it easier to understand some of the, or to establish some of the subsequent, theorems and statements that I'll make. And I want to address one question that always kind of comes up when I mention this, which is, we're talking about why are we doing optimal transport? Well, the idea is I could have picked any transport map, right? But there are a ton of transport maps from sigma to mu. So if I don't have some principled way of picking one transport map out of that, I could be in a situation where I do the same, I think about the same sigma to mu twice and pick two different transport maps. Like I need this kind of, I need a decision, a rigorous decision on which transport map I'm picking. And it just so happens picking the optimal one is a straightforward way to do it. Okay, so what this motivates is actually a notion of what I'm going to call compatible transformation. So a compatible transformation is basically a family of actions that I can do to mu, such that if I push forward mu and then do the LOT embedding, or if I do the LOT embedding and then apply this push forward, this function, I get the same thing. Okay. So examples of this, as I was just saying, are shifts and scalings, global rescalings. Okay. These are compatible transformations. And the reason this is nice is the following. If I took some convex set or something within a convex hull of functions that were compatible with my LOT embedding, then what we can do is we can take the convexity from shifts and scalings, the family of shifts and scalings, and push it forward to the convexity in the LOT space. So now what I have is a bunch of shifts of a distribution, a bunch of scalings of a distribution. Say a convex set of shifts and scalings. And then you do the LOT embedding of all of those distributions. That is also going to be a convex set in this Hilbert space. Okay. Which is very useful, as I'll say in just a sec. But then also we talk about this idea of almost compatible, because saying it's truly compatible is tough, right? In fact, Akram and Gustavo actually show, I think, shifts and scalings are the only things if you make no assumptions about anything else. Okay. But we can have almost compatible transformations. So you don't get the same thing, but they're not too far off. So you can think of these as perturbations, right? Small deformations of your distribution. Okay, this is a much richer family of transformations. And you can establish something pretty similar, which is that if you had some convex set of perturbations that was delta compatible with LOT, then when you do the LOT embedding, the set you get is going to be 2 delta convex. So 2 delta convex means it's not actually a convex set, but if you put a 2 delta tube around it, you'll be convex. Yeah. So with these in mind, we can sort of talk about this whole family of transformations we can do to a measure that are going to interact nicely with optimal transformation. Shifts, scalings, combinations, perturbations according to some metric on the original space, right? On the RD. Okay. So, by the way, if this is of interest to you, I should just note, we call these perturbations, but there's a really interesting question that came up the last time I gave this talk, which is, are there interesting deterministic functions in that set? like maybe there's actually some really rich set of transformations that are very deterministic that still are almost compatible. I'm not sure. It's actually kind of an interesting question to look into. But so for now, I'm just thinking of these as deformations and perturbations and random stuff. Okay. All right. So set up all of this framework. What's the point? So the point is to actually establish that the LOT embedding behaves nicely in certain settings. Okay. So what do we get? Say your base measure, sigma, your reference measure, and maybe a thing, a target measure or something, tau, they satisfy these what's called a Caffarelli regularity assumptions. It means they're, absolutely continuous convex supports, very nice distributions. And then you have some epsilon perturbations of compatible transformations. Then it winds up that if you did any one of these transformations to tau and any other of these transformations to tau, and did the LOT distance, just the distance in LOT space, and compared that to the actual Wasserstein distance between these distributions, you actually have Halder 1/2 regularity in terms of the amount of the perturbation. Okay, so what we're getting is when we do this embedding, if we're focusing just on elementary transformations and perturbations, is an almost isometry. Okay. So, and also I should note, right, if you're only dealing with shifts and scalings, it is an isometry. Okay. So this is nice, and also kind of says that, all right, we didn't really need to worry about centering, we didn't need to worry about rescaling, shifts, scalings, small deformations. Those don't really affect us too much. We maintain the Wasserstein geometry. Okay. Yeah, and I should say, I mean, a lot of this borrows from a paper by Geely that sort of establishes certain conditions like this on transport maps. We're sort of generalizing it to include shifts and scalings and saying you could shift really far away and it actually doesn't affect this map at all. Okay. And then I should also say, if we drop out the assumption that tau satisfies all of these conditions, you can actually still establish Halder regularity conditions. Okay. And these constants are sort of slowly being improved in the optimal transport community. And the nice thing is that as they're improved, you can kind of lift them into the machinery we have and include them to better this bound. Okay, so that's nice, but this doesn't talk about learning. So I want to get to the actual idea of learning. Okay. So say we had a distribution and a bunch of transformations of it, and another distribution and a bunch of transformations of it. Those sets of transformations ensure that these two families are disjoint and also have a little bit of a minimal separation. Then it winds up that when we embed all these transformations and all these distributions in LOT space, there's actually a linear separator between the classes. Okay, so if I'm giving all of these sets, label 1, and all of these sets label -1, I can build a linear classifier that will perfectly classify. And this comes from that convexity that I was saying that compatible transformations maintain. And I'm being a little vague here in terms of the exact constants and the exact assumptions, because under different assumptions, you get different constants, you get different orders of how strong the minimal separation has to be. We can be explicit with it in settings of, perturbations of shifts and scalings. You can write down everything explicitly. Okay. So this says that actually it might not be too bad to build a classifier between distributions. Okay. So I want to say one other comment about this, which is that since we've actually we've actually improved this quite significantly by improving the set of compatible transformations. Okay, we can actually move way beyond shifts and scalings in the following way. Let's say that sigma is not just some arbitrary thing, a Gaussian floating in the middle, but we tailor it. Maybe it's a element of, it's an example of a mu or something, right? Then it winds up, there's a lot more transformations we can do to mu and still have compatibility. Namely, if we looked at the transport map from sigma to mu, took its Jacobian, take the eigen decomposition of that Jacobian, we're actually going to be allowed to vary in those eigen directions pretty significantly, and still that's a compatible transformation. Okay, I have a picture of this in just a second that'll hopefully help. But what this suggests is if we picked a reference distribution that actually kind of mirrored our data a little bit, you can do a lot more. Which also motivates the question of what happens if you have multiple references, right? So you build the optimal transport to reference 1 and the optimal transport to reference 2, and now that's your embedding. And we have an amount of theory to basically establish all of the conditions I just said about distances, linear separability still applies in these settings, right? So the certain deformations I'm referring to are basically, like I said, these eigen directions, right? If you're going in this direction and mu1 was also in this direction, then we can also sort of shift pretty strongly in those principal directions, and that's still compatible. And then similarly, we can have this idea of multiple references, and you just stack the reference, the transport maps next to each other, and that is now your LOT embedding for multiple references. And there's this really nice thing that if you're linearly separable with respect to one of them, then you're linearly separable. So it works out. So this is some of the theory that we have, but I want to motivate why this is useful and go through some experiments. I'll go a little quickly through this. I know it's very late for you. I apologize for that. But anyways, so how does this work in practice? Like basically what we're saying is, let's say we have some classification model where we want to be invariant to shifts, scalings, epsilon perturbations, things like this. Well, then what we can do is we can build our LOT embedding, and now we have convex sets that are linearly separable. So just build a linear classifier in that space, and you've classified the distributions. Okay. So I want to mention, right, these are functions, and I was talking about communication. So obviously this is a little complicated, but it winds up in practice, what you can do is you can sample from or discretize your reference distribution in order to get this function down to some finite dimension. And then similarly, because we only care about basically pairwise Euclidean distances, we could actually then further reduce that quite significantly by doing a JL embedding of all of these, right? Because we only need to maintain pairwise distances, and we could still build a linear classifier. Okay. So then through some JL embedding, you can actually reduce this representation quite significantly, and still, establish some pretty nice results. So I'm going to give a couple of examples here. I'll go through these quickly. Let's just pick like a toy problem. Say you want to classify 1s from 2s in MNIST or something, right? Like I said, you can think of those densities on the unit square. I want to make the problem a little bit harder. Let's say along with just having different examples of images, I rescale them. So some of them are really tiny and some of them are really big. And I shift them around. So you have a tiny one over here and a huge one over here and a tiny 2 in the middle and a huge 2 over to the right. Okay. So they're not just nice and simple centered, right? In that setting, what you wind up getting is if you do the LOT embedding of all of these things and try to build a linear classifier, since linear classifiers, you don't really need much training data. It winds up that if you just had, 60 examples, right? Labeled examples randomly chosen from this harder problem of deformations of 1s and 2s, you can still build a classifier that does incredibly well. And I should note, this does better than if you did some PCA embedding of these. This does better than if you did some, convolutional neural network where you're trying to figure out how to classify these. It works really well in a small data regime. And I should also say you can shear, right? So we have examples where classifying 7s and 9s, and you want to shear these things in certain directions. Okay. And these shearings can actually be quite severe. And it still winds up that you get a pretty good classifier by building a linear classifier in the LOT space. Okay. So I have one last experiment I want to show, just because I kind of promised like what motivated me into this problem. So if you see me giving talks before, I maybe have mentioned flow cytometry previously. I used to work on this for unsupervised problems, but now we can do this for supervised problems. So flow cytometry, basically somebody draws your blood, treats it with some chemicals, drops it through some system. Each cell then gets like a 9-dimensional representation. Okay, so now a person is a 9-dimensional point cloud, right? You know, of 50,000 points or something. And this is how medical doctors actually diagnose blood diseases like leukemia or AML, which is a very deadly form of leukemia. But these point clouds are not easy. I mean, this is a point cloud. This is a 3-dimensional slice of a healthy person. This is a 3-dimensional slice of a sick person. Winds up the thing that you're really keying in on is that like this L shape is very defined here, whereas in the AML, it's a little more blobby. That has to do with like how white blood cells are aging or not aging for AML. And honestly, the way that a lot of classification on AML works is by looking at 2D slices of this 9-dimensional object, literally looking at them, and then doing what's called gating, which basically removes some of the cells, and then you look at some subset of the cells in 2 dimensions. But these are, you know, high-dimensional point clouds. So let's try to build a classifier on them, right? So we can just pick a uniform reference distribution, you know, in the space, build these LOT transformations, LOT embeddings, take PCA of all of them to reduce to 25 dimensions, and fit a linear classifier. Okay, this is on real data. AML is an easy problem, quote unquote, to discover as far as like flow cytometry goes, but this is still a pretty, you know, involved thing. And what we get is if you only train with 15 sick people and 50 healthy people and test on the rest of the population, phenomenal classification, right? This is a 2D embedding. You know, you basically make sure that you preserve this SVM here. You can see these things really are linearly separate, right? So this is, you know, preliminary results that we're building on, but I think that this LOT embedding framework really has a lot of potential to help build really nice ways to classify to point clouds and distributions. We have some examples about active learning that I won't go into for now. So I'll go ahead and end here, but basically, you know, what's the idea, right? When you know what whenever you do, if you want to do optimal transport to a fixed reference, it actually opens up a very rich set of features through that transport map with which you can do classification. You can approximate distances without having to compute as many optimal transport calculations. You know, and so different directions we're going currently is, you know, linear separators are really easy to learn. You can learn them through active learning, which is where you query the labels as you go. And so we're building on this currently with a student of mine. You know, a downside of this is that optimal transport, even on N embeddings, is still expensive. So direction of research that we're going to put up a paper shortly on is how to do this same type of stuff for entropic regularized optimal transport or Sinkhorn optimal transport. You still get a lot of very nice guarantees, but each one of those N can be computed quite quickly. So that's the idea. Here's some papers if you're interested in talking about it further. And yeah, thank you.